Exam, so we'll make our way through this a bit together. I'll probably, like, my aim would be to do all of it, but we'll see how you guys are feeling about it. If there's stuff you want to just skip over, let me know. But my assumption is that we'll try and crank out all of it, and we'll try aim for sort of 40, 45 minutes. Yesterday we spoke about, every night, okay, leaning yourself one way or the other, It's just a matter of doing 3 or 4 questions every night, as a bare minimum to prepare yourself for the exam. So it's not about just cramming in the week before, it's about, we start now, and it's just a little bit at a time. Okay, so I remind you to do that. Okay, so here we have question 9. We have 2 graphs, ln of 5x and ln of x. And we've got a point when x is 2 on f of x and when x is 2 on g of x. And it says, what is the exact distance between the points A and B? Okay, so this function here is ln of 5x, and this function here is ln of x. All right, now the distance between these 2 points is going to be that y value, take this y value. Okay, you can think of the distance between them. They have the same horizontal location, all right, but there's a vertical distance between them, so it's the top y value, take the bottom y value. So in fact, for any value of x, the distance between them is the top function, take the bottom function. For any value of x, that's going to be the distance between the 2 functions. Now we're talking specifically about when x is 2. So we have ln 10, take ln 2, and we could write that as ln of 10 on top of 2, which is ln 5. All right, so 2 marks just for saying the distance between them is ln 5. Oops. Okay. Part B. Find the value of x such that g dash of x equals 2. So g of x is ln of x. G dash of x is going to be 1 on x. And if we have 1 on x is 2. Okay. So the long way to solve this, okay, the long way to solve this is to go times both sides by x. So you need to get 1 is 2x. And then divide both sides by 2, so you get x is half. All right. The only reason it's a longer way is because there's an extra step. A better way to think about it is we can do anything we want, right, as long as we do it to both sides. Now over here we have 2 on top of 1, and here we've got 1 on top of x. So one thing we can do is just perform the reciprocal of both sides. That is, we just flip them. So this becomes x on 1, and this side becomes 1 on 2. And you can see it generates the same answer. Right, you can see the answer from looking at it. We need to perform the reciprocal. All right, but it's a two mark process to just generate that solution. X is half. Okay, let hx equal ln kx, where k is greater than 0. So that's h of x. Okay, find x such that h dash of x equals 2. All right, so we have h of x is ln of kx. All right. Differentiate it, okay, so h dash of x is going to be k on top of kx, okay, which is 1 on top of x. And then find the value of x when 1 on x equals 2. Well, that's going to be half again as well. All right, and you can see it flows on part 1 and part 2. Part 1, find it for x. Part 2, what's the link here? Okay, part C. Comment on the relationship between the graphs of ln of x and ln of kx. Okay, so looking at, here we've sort of got an example of it. We've got ln of x and ln of 5x. You can see they have the same sort of shape, all right, but one's sort of a little bit different. So there's 2 ways we could think about it. The first way you might be tempted to think about it is just with a general function. Remember, if we have a f of b times x takes c plus d, all right, that c and d affect horizontal and vertical translation. Okay, so it's not that. A and b affect vertical and horizontal dilation, so they're stretching and compressing it. So you could look at that and go, that's affecting horizontal dilation, and so this number out the front just affects the horizontal dilation. That could be one comment we make, right? But I think a better way to think about it with these ln functions, okay? If we have ln kx, right? One way we could write this is ln k plus ln x. Right, we can split it. Remember, ln of A plus ln of B is ln of AB. So we can start with a product and do the opposite. We can go back that way. And now you can see, okay, it's the same function. If we're thinking of what's the relation between ln x and ln of kx, it's the same function, but it has this ln k. What is k? K is a number. What is ln k? It's a number. So it's just the same function, but with this vertical translation of ln k. All right, so two ways of thinking about it. We could think of it as a horizontal dilation or as a vertical translation of ln of k. So what does it say? Comment on the relationship, okay, between g of x and h of x. All right, so h of x equals, let's just put it like this, g of x plus ln k. All right, so that would be a mathematical way to describe it. All right, or we could say h of x is a vertical translation of g of x by ln k units. Cool, let's flip the page. We're talking about sheep. We're calculating confidence intervals. So this is what it's going to be like. It's going to be like fat text. Okay, there's just like, look at all that information there. Let's pick out what's the important stuff. Okay, that doesn't mean you read it as fast as you can though. Okay, you'll read it slowly, comprehend it. The quality of sheep's wool is based primarily on the average diameter of its fibres, measured in microns. A wool producer wishes to make a claim about the average diameter of fibres in one bale of wool, sourced from one flock of Australian merino sheep. Historically, the wool sourced from this flock has a fibre diameter that is normally distributed with a standard deviation of 2.5. The wool producer chooses 80 fibres randomly from the table, then measures the diameter of each of these fibres and calculates the sample mean as x bar 80. So the sample average from 80 pieces of data is 17.4. So let's list the sort of information we've got so far, and like maybe you're going to highlight it when you're doing it. 17.4, we have a standard deviation. This is the historical standard deviation of 2.5, and make sure you have the same unit, okay? Because that sometimes they'll give you stuff in grams and stuff in kilograms. All right, that's sort of a way of just checking that you're, that you're reading it and comprehending it. So make sure we have the same unit, and we have n is 80. We've sampled 80 fibres. Okay. Based on this sample, calculate the 99% confidence interval. So I'm just going straight to my calculator and I'm just going to put that in my calculator rather than trying to do it manually. So for a confidence interval, we go into statistics, we go test z first sample. Alright, and we'll put the information in there. We need to make sure our data, no. Sorry, it's not test, it's interval. That's better. Test interval z first sample, and we can put all the information there. Now we want 99% confidence, so we're going to put 0.99. Our standard deviation is 2.5. Our number of samples is 80, and our observed mean is 17.4. 80 and 2.5. Okay, and so then we're just making a single statement here for part A. All right, we've got 16.68 is less than the mean, the true mean. Okay, we're using x bar to indicate us what the true mean is, which is less than 18.11. Okay, so I've got 4 figures there, and we've said, does it tell us to? It doesn't tell us to round it to a certain amount, so we'll just go for 3 significant figures. So I've said there's 2 ways of doing it, okay? To guarantee that level of confidence, you can round the bottom end down and the top end up, or you could just round it normally, okay? They're going to accept either, but if you do the first one that I said, make sure you put that as a justification. That's the way you've rounded it in order to guarantee the confidence. That being said, you're not going to be penalised for just rounding it normally. So we've got 16.7, the mean, and 18.1. Okay, so it lies somewhere in there. Excellent. Part B. Based on this sample, the 95% confidence interval is 16.9 to 17.9. Okay? So here we have the 99% confidence interval. So let's just put a number line up here to compare them. So we've got sort of 16, 17, 18, 19. All right, so this is our 99. It goes from 16.7 here, 16.7 to 18.1. That's the 99% confidence interval. And then the 95% confidence interval is from 16.9, so that's like here, to 17.9 here. So it's a narrower window. All right, I think that's what the question's alluding to. Explain why, when based on the same sample, a 95% confidence interval is wider than a 90% confidence interval. Okay, so it's asking about a 90% confidence interval. Okay, so like if we were to calculate the 90% confidence interval, and you could go ahead and do that by just changing this number to 90 in there when we perform that confidence interval, what you're going to find is it looks like this. Okay? And that's something we described to you guys when we were talking about confidence intervals, that the more confident you want to be, the wider the margin is going to be in order to guarantee that level of confidence. So what are we going to say here? Why is a 95% confidence interval wider than 90? Okay, let's try and articulate that as best as we can. In order to guarantee a 95% confidence level, the lower end and the upper end, what we call them, the parameters of the need to be stretched to guarantee this level of confidence. Okay, so let me give you a little hint as well for when you're writing those things, okay? So it can be a good idea because no doubt you're going to have some time at the end, all right? I've never had a student come out of the exam and say, gee, I was really rushing for time there. They always find there's lots of stuff that they sort of don't know how to answer, and so the stuff that they do know how to answer, there's lots of time to answer. Okay? So one way we should think about answering these questions, all right, is you've got some scribble paper, jot down the first thing that comes to your head. Okay? And if you jot down the first thing that comes to your head, then when you go to write it on paper, you have something to inform your decision. It's like writing an essay, right? You start with something crap, it's about just putting some words on paper and then refining it so that it's in its most sort of articulate and clear form. Okay, let's proceed. So I'm spending too long here just chit-chatting. Part C. Based on the sample, the wool producer labels this bale as having an average fibre diameter of 18 microns or less. That might be problematic because we're thinking about our confidence interval. 99% confidence interval was up to 18.1, wasn't it? The manufacturer can make a claim with K% level of confidence if it is supported by a confidence interval. With reference to your answers in Part A and information provided in Part B, what can you conclude about the confidence with which the wool producer can label this bale of wool as having an average diameter of 18 microns or less? Okay. Well, they can't use the 99% confidence interval. Okay, why? Because according to the 99% confidence interval, the mean could be as high as 18.1. Alright, so we can't use 99%, but we can use 95 because according to the 95% confidence interval, the mean could be as high as 17.9. Okay? In fact, you could even stretch that out a little bit more. So to answer this part, there is some level of confidence between 95% and 99% that the wool producer can use, okay? But it's somewhere between 95 to 99. They don't ask us to calculate it. So I'm going to get a new marker because this one's had enough of it. Okay, so part C. And so that we can see that based on this image here, that's a pretty good way to communicate it as well. So the wool producer cannot use 99%. Okay, I'm just going to put dot, so I'll set it out loud. Cannot use 99% because according to the 99% confidence interval, the true mean could be as high as 18.1 microns, which contradicts the claim. Okay, the wool producer can use the 95% confidence interval because, according to it, the highest the true mean could possibly be is 17.9. So if we're making a point like that, it's somewhere in between the 95 and 99% confidence interval. So then this wool producer is just like making ridiculous claims, aren't they? What is the maximum level of confidence the wool producer can label this bale of wool as having an average fibre diameter of 17.5 microns or less? So let's build an argument up for this one, because there's solid 3 marks here. Okay, so let's think about a confidence interval, right? Times the standard deviation on the square root of anything. That's 80. Okay, so that's the formula for the confidence interval, right? Now, if the wool producer is going to make the claim that it is 17.5 or less, all right, that means the top end of their confidence interval is 17.5, okay? This is the calculation for the top end of the confidence interval. So what we're going to do is we're going to solve for Z alpha on 2, all right? We've got 17.4 plus Z alpha on 2 times 2.5 on the square root of 80 equals 17.5. We're interested in this value here because that tells us the level of confidence. Remember, 95% confidence, 1.96. Okay, 99% confidence, what's it like, 2.56 or something? Okay, so let's solve this. This is just a variable, and we're just going to move everything around until we isolate Z alpha on 2. So we have times 2.5 on the square root of 80 is going to be 0.1. Okay, we'll take 17.4 from both sides. And then I'm just going to multiply both sides by root 80 on 2.5. Okay, so if we did it over here, 2.5 at the top, bottom, and cancel, same with the root 80. So when we calculate that, we get 0.1 times root 80 on top of 2.5 or 3.5. We've got 0.357. 877, so I'll round it. Okay, so let's remind you of what that value means. So remember, in a confidence interval, right, when we do 95% confidence interval, it's covering 95% of the distribution. Okay, so that's 95%. And the value 1.96 means 1.96 standard deviations below the mean and 1.96 standard deviations above the mean. So our question is, rather than covering 0.95 of the area, 95% of the area, we're covering 0.358 of the area. So it's like, it's not very confident at all. It's like maybe this much, 38.5% of the area. And we're saying, what is these values? Let's call them K. Okay, so that's minus K, that's positive K. All right. Sorry, I mixed that up. This is the value of K, 0.385. And that's 0.385. And this is going to be our level of confidence. Okay? This is the Z-score, that's why it's Z alpha on 2, the Z-score that guarantees that level of confidence. This is the Z-score that guarantees 95% confidence. Okay, so this is going to be the Z-score that gives us the level of confidence we're interested in. So how am I going to calculate that? Well, that's just there's a couple of ways. Okay, it's just a normal distribution calculation. Okay, it's NCD. Our lower boundary is minus 0.385. Our upper boundary is 0.385. Our standard deviation is 1, and our mean is 0. It's a Z distribution, isn't it? We're saying what level of confidence does this value of z give us? So 0.388, not 85, is it?
It says 5.8 on your board.
358, is it? Thank you. I was mixing them up. Alright, so that should be 5. Alright, 0.358. So lower, make sure it's negative. Standard deviation 1, mean 0. We've got 27.9% confidence, 27.96% or 28% confidence. Okay, so if they want to use that number, 17.4 microns, 17.5 microns, they can only guarantee it with 28% confidence. All right. Okay. Does anyone want to ask anything about that? That's like a little bit tricky. Okay, another way you could get this solution would be with trial and error. Right? How could you get it with trial and error? That's if you're doing confidence interval calculations. Okay, so we're following this procedure along here. You're just going straight to your calculator. And the only thing you're changing, you're leaving the number of samples as the same, you're leaving your observed observation as the same, standard deviation is the same. The only thing you're changing is your confidence level. Okay? And you just keep changing your confidence level until you get the top end of your confidence interval to be 17.5. Okay? So that would be another way.
Would you get all 3 marks if you did that then?
I believe so. Yeah. Yeah. Because they don't tell you a procedure you need to follow.
So you just keep changing that up and down until it...
Yeah, yep. And what if you did it first and you put 60% confidence, you'd see it's still way above 17.5, so that'd give you a hint on 30%. Alright? But I think you're getting marks there for interpreting what they're asking me to do. Okay? So, how about question 11, right? So you've probably seen this pop up in a few practice tests and so forth. Happy to do it, unless you want to skim over it.
No.
Yep, Austin's keen. Yeah?
Yeah.
Yeah, let's do it.
We need to do this.
Yeah. Austin's keen. Okay. So we have a major city has a wet and dry season, and the manufacturer in the city makes umbrellas and sells these umbrellas throughout the year. The rate of sales is not constant. Based on the sales data, the rate at which they're sold can be modeled by the function. T is time in months. There's the graph. For what values of T is the sales at a minimum? Okay, so you could go straight to your calculator and G-solve them in. Here you can read off the graph as well. Just says for what value of T, we just need to answer T is 6. Okay, part B part 1. Calculate how many umbrellas were sold during the first 3 months of 2016. All right, so what we have on this graph, I'll bring up this question to us. Okay, this graph is the rate of change, and so we always know that area under the curve of a rate of change graph is going to tell us quantity. So it wants us to calculate the area under the curve from 0 to 3 of the function. And I'm just going to put f of t for shorthand, right, save a bit of time. And all you need to do is just calculate that. All right, obviously we're not using fundamental theorem of calculus, look how much space is there. All right. So if we're going to calculate that, what I'm going to do as well, rather than putting it in RunMap, okay, I'm going to graph it because I'm thinking this is a graphing problem. I'm probably going to be using the graph throughout the rest of the question. It makes sense to graph it now, save a bit of time. So we've got 750 cos pi on 6 x plus 150 cos pi on 3 times x take 3. Okay, and they've even given you a bit of a V window there, so just copy them, their x and y, so x from 0 to 20, y from 0 to 2000, that's helpful. And make sure it's on radians as well. There we go, looks beautiful to me. Okay, so to perform that calculation, I'm just going G solve integral from 0 to 3. Lower boundary 0, upper boundary 3. Remember, we can perform them on our calculator. So it's working it out. 4,432. Now, are we told to round at all? Just as calculate. 32.3, so to the nearest whole number, 4,432. Okay, part 2. Indicate that information on the graph. That means shade the area. All right, so you draw the line at the 3,000 there, at the 3 months there, sorry. Indicate that on the graph. Okay, the manufacturer produces 1,000 umbrellas per month. Draw this information on the graph. All right, so it looks like this, doesn't it? Okay, now this is the rate at which umbrellas are being sold. Okay, so the point of the question, right, is that we have rainy months and we have dry months, and obviously we're going to sell more umbrellas during the rainy months than we will during the dry months. That's the point of what it's saying. And it's saying this factory, though, this factory makes 1,000 umbrellas per month all the time. Okay, so in January they made 1,000, in February they made 1,000, in what comes up February, March they made 1,000. Right? The rate is always the same. Okay. Whereas notice here with sales, the sales are sort of coming and going, sort of undulating depending on the season. Cool. Okay, when the manufacturer produces more umbrellas than they sell, the surplus umbrellas are stored in a warehouse. And when they produce fewer umbrellas than they sell, the umbrellas that are stored in the warehouse are sold. Okay? So for instance, during this period of time, right, okay, they're not selling many umbrellas. In fact, they're making more umbrellas than they're selling. All right? But during this period of time, they're selling more umbrellas than they're making. Okay, this is how many, they're always making 1,000. And up here, you know, if we look at the most that they're selling at the start, that's like 1,600 umbrellas a month, while they're only making 1,000 umbrellas a month. So they're sort of, they're not the same. They're not the same. Okay, part D. When time is 10, which of the following is happening? Tick the appropriate box. So when time is 10, that's sort of here-ish, isn't it? That's here. So let's consider what is happening during this period of time. The two options are the number of umbrellas stored in the warehouse is increasing, or the number of umbrellas stored in the warehouse is decreasing. At this point in time, okay, this function is how many umbrellas are being sold, okay? At this point in time, more umbrellas are being sold than umbrellas are being made. We only have 1,000 umbrellas being made, and we have, based off the graph, about 1,500 umbrellas being sold a month, okay? So there's more umbrellas being sold than are made, which means they're taking them from the warehouse in order to fill in the gaps that they have in production. So what that means is the number of umbrellas stored in the warehouse is decreasing. That's our second option. Okay. Decreasing. Part E. Show that the manufacturer sold the same number of umbrellas as they produced over the 12 months of 2016. Okay? So, well, the number that they sold is going to be the integral from 0 to 12 of f of t. Alright? So we can calculate that. And the number that they made is going to be the integral from 0 to 12 of 1,000. Okay? 1,000. The equation of this line here is y equals 1,000. It's a horizontal line. Y is 1,000. And so if we calculate this, let's do that. G solve. Integral from 0 to 12. Shades the whole area for us, and we'll get 12,000 umbrellas sold. And then if we do that, integral from 0 to 12 of 1,000, well, that's just 12 times 1,000, that's 12,000 produced. Okay, so that's a suitable way of showing that. During 2016, for what values of T were the number of umbrellas stored in the warehouse increasing? Okay, so we've noted that in this part. We basically said whenever this function is above the line, more umbrellas are being sold than are being produced. Okay, so what that means is when it's above, the number of umbrellas in the warehouse is disappearing. So that means when it's below, that's when they're increasing their stock. Okay, because what's happening is they're making more umbrellas than they're selling. And so the number of umbrellas is increasing. So that's between this period of time and this period of time. I think the best way to find that, we're going to graph this function, y is 1,000, so I'm going to put that in, and then I'm just going to g-solve this point of intersection and this point of intersection. G-solve intersect 3.35 7 and 2 8.642. So if we round that, 3.36 is less than t is less than 8.64. So that's when the number of umbrellas is increasing, okay, between the 3rd month and the 8th month, okay? During that period of time, we're making more than we're selling. So there's more umbrellas being made than being sold. Okay, when time is 0, the warehouse has 5,250 umbrellas. So when time is 0, at this point in time, let's make a note of that. T is 0, 5,250 umbrellas. Okay, during 2016, what is the greatest number of umbrellas in the warehouse? During 2016, what's the greatest number of umbrellas in the warehouse? Okay. So let's think about it. During this period of time here, from there to there, that's like 3.3, and here's 8.6. Okay, from there to there, the number of umbrellas is decreasing because we're selling more than we're making. Okay, and then the number of umbrellas starts to increase, and it's the number of umbrellas in the warehouse is increasing all the way up to this point in time. Okay, and then after 8.6. more umbrellas are being sold than are being made, and so the number of umbrellas in the warehouse starts to decrease. So that means the most amount of umbrellas in the warehouse occurs at this point. All right, so I'll just say that again. So if we follow along here, this is when the number of umbrellas being made is more than being sold is more than are being made, and then during this period we've said this is when they're increasing. And then they stop increasing, the number starts decreasing. So we know that from our answer here, that this is going to be when there's the most umbrellas in there. We know there's initially 5,250, okay? So initially there's 5,250, but we're going to take away how many we sell from 0 to 8.64 of the ones we're selling, but then we're also adding in the ones we make, okay? So we have the amount we started with. This is how many we've sold since time is 0. From 0 to 8.64 months of how many we're selling, and then plus how many we've made. So we've got some in there, we're getting rid of some, we've got some more coming in. How many are we left with? So it's going to be a bit nasty to calculate. So we've got 5,250. So I know this calculation, right? That's just going to be 8,640, so I can see that part. So we've got 5,250 plus 8,640, and then we've got to take away however many we sold. So that one is not going to be too hard to calculate. G-solve integral from 0 to 8.64. And we sold 7,180. So we're just smashing that together. $3,710 umbrellas. Okay, we're moving a little bit slowly, but that's because we're going into lots of detail. That's okay. So what do we got? We've got 12, 13, and 14. So, like we'll do 12. People pretty happy to do 12? Yeah. Okay. We have the distributor of a particular seed claims that on average 60% of seeds are viable. That means they're going to grow into seedlings. let x be the random variable when we're planting 8 seeds. State the distribution of x. Okay, so x is a binomial distribution, and we have, when we're doing binomial, we have n then p. Okay, we can contrast that with a normal distribution. Okay, x is normally distributed with what's it? Mean and then standard deviation squared. Okay, so this is a binomial. The number of samples, the number of trials is 8. We're planting 8 seeds, and the probability that a seed will germinate is 0.6. Okay, so that's what it means to state the distribution. Okay, out of repeated plantings, what is the expected number of viable seeds? Okay, what is E of x? So we can also think about it like this, right? Okay, we have the events and then the probability of the events occurring. Okay, 0 is the probability that a seed, out of repeated plantings of 8 seeds, what is the expected number of viable seeds? NP. N times P. Okay, so that's going to be 8 times 0.6. So what's that? 0.8 and 6 of them. 0.48. 4.8. Okay, part 3. The table below shows the probability for Ks 0, 1, 2, 3, and then they've even given us 7, 8. Complete the table for Ks 4, Ks 5, and Ks 6. Okay, there's a couple of procedures we could follow. The simplest is going to be, it's a BPD calculation. All right, so we're talking about what's the probability that 4 seeds germinate out of 8 with a probability of germinating of 0.6. Okay, and then for 5 seeds, what's the probability that 5 seeds out of 8 with a probability of 0.6 germinate? Okay, and so that's how we're going to fill in this table here. So I've got Ks 4. 8.6 gives me 0.232, and then 5, 8, 0.279. Okay, and then 6 as well, 0.209. Cool. A gardener plants 8 of these seeds in his garden. What is the most likely number of these seeds that will be viable? Okay, what is the event there with the highest probability? 5. What is the probability that 6 or fewer? 6 or fewer. So this is, what's the probability of x being less than or equal to 6? So they're saying 6 or less. Okay, a couple of ways this could be done. You could look at your table and go probability of 6 plus probability of 5 plus 4 plus 3 plus 2 plus 1. Okay, or we can just do a BCD calculation. From 0 to 6, out of 8 seeds, what's the probability of at least 6 germinating? Distribution, binomial BCD, 89%. Okay, farmer bought a large bag of these seeds. She planted 100 from the bag and observed that 53 were viable. Okay. Calculate the proportion of seeds that were viable. Well, P, remember the observed value of P is the number of successes divided by the number of trials. X on there. We've got 53 on the 100, 0.53. Look at these easy marks we can pick up here. Calculate the proportion, done. Calculate the 95% confidence interval for the proportion. Okay, so we'll follow a similar procedure to the one we did. I've rubbed it out now, but it's in statistics. Interval Z first proportion. and they've said 99% confidence interval, 95, sorry. We have 53 successes out of 100. 0.432 is less than P, which is less than 0.628. All right. So that's part 1, part 2, part 3. Based on the confidence interval, can it be concluded that the distributors claim that on average 60% of seeds are viable is false? No. According to this confidence interval, the true proportion could be as high as 62.8%. So the distributor is justified in making this claim. It's within the confidence interval. Okay, part 4. Part 4 is getting you to think about confidence intervals and so forth. So yeah, part 4 there. Alright, so I'm just looking at the formula sheet here. So this is the formula for a confidence interval for a proportion. So it is P hat, take our value of Z out on 2, in this circumstance 1.96, times the square root of P times Q on N. So that's how we've generated this, right? Is less than P, is less than P hat, plus 1.96, square root of P hat, Q hat on N. Alright, now this question here, it says show that N, given an estimate of P star, show that the sample size N required to obtain 95% confidence interval of the following proportion is. Okay, so they're giving us a formula, and that's one that we sort of have in our textbook already, one that we've talked about. This is a way you can calculate N. Alright, how have they generated that formula? Well, let's think about it, right? The width of a confidence interval is the upper boundary, take away the lower boundary. Okay, that's how wide the confidence interval is. The upper boundary, take the lower boundary. That's how we generate that formula for the width. What is the formula for the width? It is 2 times 1.96 square root P Q on N. That's the formula for the width. Okay? And the way they generate it is by doing the top, take the bottom. And they're saying using the width formula, rearrange it to get N by itself. Okay, we want this variable N by itself. So we're going to crunch an algebra here for that. So first what I do is I divide both sides by 2 times 1.96. I hope everyone at the back can see. I'm going to sneak it in here. So we've got W on 2 times 1.96 equals the square root of PQ on N. Okay, then we would square both sides. So we have P W on 2 times 1.96 squared equals PQ on N. Reciprocal both sides. We're looking to get N by itself, aren't we? So sorry, 2 times 1.96 on W equals N on PQ, and then times both sides by PQ. That is bringing PQ up here. Okay, and then you've got the solution that it's looking for there. Okay, part 5. The farmer wishes to reduce the uncertainty in the estimate in her bag. Using the information in C part 4 or otherwise, calculate the smallest number of seeds that she would need to plant in order to have a confidence interval with a width of 0.1. Okay, so they're saying using this formula, using the formula from the part you just had above, alright, so they've listed it there for us. Width is 0.1, everything else remains the same, okay? So they're giving us two options here, Okay, we can use the value of P that they gave us, 0.53, or you can use P in the worst case scenario, okay? The worst case scenario for a proportion is when P is 0.5. That's going to create the biggest confidence interval. That's always been the case, okay? So two options, we can use 0.53 or 0.5. They'll mark both as correct. Okay, calculate the smallest number of seats. So let's perform this calculation. We've got N is 2 times 1.96 on top of the width is 0.1 squared, and then I'm just going to go with the 0.53 and the 0.47. Okay, so I'm going to assume we're maintaining that same proportion. And we calculate that number, that's going to be our value of N here. Okay, so here we go. 2 times 1.96, 0.1 squared times 0.53 times 0.47. I've got 382.7. So in order to guarantee, we round up 380. Okay, so that's the end of that question. 250. What do you reckon?
Sleeping logs.
Say again?
Sleeping logs.
Yeah.
Say again? Sleeping logs.
Sure,
Sleeping
we'll
logs.
finish it next lesson.
So our next lesson won't be till next term. So I told you guys some more on Friday. We'll have shooting holidays. Okay?
Can we just do question 14?
Yep, let's do the conjecture. So this problem, that's a good one, that's a good point, okay? So the next problem, right, you've had a fair bit of exposure to that already. I suspect most people were sort of able to answer a fair bit of that when we did it the first time. Let's do the conjecture problem and we'll stop there. Okay, so question 14, we have these beautiful sine curves, and I know there's stuff there.
They're not even beautiful, they're squiggly.
So have a read of the question, familiarise yourself with it while I erase here, and then I'll leap straight into it. Okay. So here it is. So we have Jean-Baptiste, okay, he's got a model here, sawtooth function. This is how it develops. They give you a few examples. All right, part 1, find f dash of x. Okay, well, f of x is sine of x, take sine 2x on 2. Okay, that's f of x. Now, I've said continuously, whenever you have like sine 2x on a number, think about it like this, half sine of 2x. All right, and the reason that's helpful is because you're not going to perform some silly quotient rule when you don't need to. Okay, always think of number denominators like that. Okay, then let's differentiate. Sine x goes to cos x, the half is going to hang out, and the derivative of sine 2x is 2 cos 2x. Okay, and so that just simplifies to cos of x, take cos of 2x. Okay, that's part 1. Hence, show that when f, show that for pi, f dash of pi is minus 2. Well, f dash of pi is going to be cos of pi, take cos of 2 pi. Okay, so let's take you back to unit circle days. Alright, here's 0, 2 pi, 4 pi, etc. Okay, they're all multiples of 2 pi. And then if you keep going around the unit circle, you know, pi on 2, pi. Okay, so that's going to be pi, 3 pi, 5 pi, etc. They're not odd multiples of pi. So f dash of pi. So when x is pi, what is cos? Cos is the x coordinate. Okay, at this point the x coordinate of pi is minus 1. So we have that's minus 1. And we know when it's 2 pi over here, the x coordinate is positive 1. So we have minus 1 take 1. That's minus 1 take 1 is minus 2. Alright. Okay, on the graph, sketch the tangent. Okay, so you can Here's pi, just draw a tangent as best as you can there. Part B, find g of x. No, g dash of x. So g of x is sine x, take sine 2x on 2 plus sine 3x on 3. Okay, so g dash, look, we already know what this part goes to. We've already differentiated that. So don't even think about it. Just go, what did I get last time? Cos x take cos 2x. Okay, and then this is going to be, well, again, I've said when you have 3, think about it as 1 on top of 3. Okay, so it's going to be 1 on 3 times 3 cos 3x. So that's going to be cos 3x. All right, so that's fine there. So that's done. Find h dash of x. Okay, so we've got h of x listed there as well. It's following the same pattern. You should be able to start to recognise it. Cos x, take cos 2x, plus cos 3x. Okay, that's the part we've already got. And then I'm just going, and what's the derivative of the last part? Minus sine 4x on 4. It's going to be take cos of 4x. Okay, so you can see it's got positive, negative, positive, negative. It's following this sort of pattern. Okay, fill in the table. Alright, so here's the table. We've got f dash of pi, we've got g dash of pi, and we've got h dash of pi. We've got minus 2. Okay, the other way, right, if you put this in your calculator, cos of pi, you've got 7 ratings, it's going to punch that out for you. Same with this, alright? So if we want to know what's the slope for g, when we put pi in there, you can just put this in your calculator. Cos of pi, take cos of 2 pi, plus cos of 3 pi. Alright? This is minus 3, this is minus 4. Alright, you can just get that straight from your calculator. Alright, explain the effect of increasing the number of terms of k on the slope of the tangent. So, so you can just write as k increases by 1, the slope of the tangent decreases by 1. Alright, so you can see this is going, so we've got here, we've got k is 2, k is 3, k is 4. Well, we've got negative 2, negative 3, negative 4. So we could write it like that. Probably a better way might be as k increases, so the slope of the tangent is minus k, isn't it? Alright, so here we had k is 2, we had negative 2. Here we had k is 3, we had slope negative 3. That's a better way to say it. Explain the effect of increasing. Yeah. Cool. Okay, consider the function for k is 7. Make a conjecture about p dash of pi. So here they've got p of x, they've got this long function with 7 terms in it now. Well, we saw when k is 2, the slope is negative 2. When k is 3, the slope is negative 3. So what about when k is 7? We're going to anticipate the slope is negative 7. Okay, let r of x be a function of this type, a general function with k terms, where k is any positive integer. Alright, make a conjecture about the value of the derivative for any value of k. So we're going to say r dash of pi equals minus k. Alright, so over here we're sort of developing the pattern, we're trying to recognise it. Over here we're stating it explicitly. Alright, for k terms, the slope is negative k. Okay, part 2. Let y be the kth or final term of r of x above. Alright, so the final term, like if you follow that sequence right, you know, you've got sine x plus half sine, take half sine 2x plus, you know, if you keep following it, they're saying this last term, alright, we're saying we're not going to tell you whether it's negative or positive. Okay? It's negative 1 to the power of k take 1 sine of kx on k. Okay, this is the last term. Show that when x is pi, the slope is minus 1. The slope of this last term is minus 1. So let's just consider that part. We've got minus 1 times k take 1. Now I've told you guys to think about it like this, haven't I? 1k sine of kx. Alright, remember k is just a number. And we're saying when x is pi, what is the slope of this function? and x is pi, what's the slope of this function?
This is the domain.
Well, this part here is just a number, so that's just going to hang out. So if we want to know the slope, we need the derivative, don't we? So this is hanging out, it's just a number. We're only going to differentiate this part. Okay, so if this is y, then dy on dx is going to be minus 1, k take 1. We've got this 1 on k here, still hanging out, and the derivative of sine kx is k cos kx. Alright? Now we have 1 on k times k, they will cancel, and so the derivative is minus 1 times k take 1 cos of kx. Alright? Now we're saying when x equals pi. Okay, when x equals pi. Now it's not enough to just take pi and plug it in there, because if we have, if we think of k being positive 2 or 4 or 6, then this here is going to be positive 1. Alright? And if we think of k as being positive 1, positive 3, positive 5, odd numbers, this is going to be negative 1. So we need to consider two cases here, and this is the trick to this question. We're going to say when k is, let's do even first, because they're probably a little bit easier to investigate. If k is even, okay, let's evaluate the derivative if k is even. dy on dx is going to be minus 1 to the power of, and even numbers like, so 2 or 4 or 6, okay? If we have 2 take 1, this is going to be an odd number here, all right? If we have 4 take 1, it's going to be 3. If we have 6 take 1, it's going to be 5. Point is, this is going to be an odd number, and so minus 1 to the power of an odd number is minus 1, okay? So we've successfully evaluated, if k is an even number, when k is even, this part is negative, okay? That's important, this part's negative. How about this part? We've got cos of kx. Okay, well you can think if k is an even number, so we've got positive 2 pi, positive 4 pi, positive 6 pi. Okay, it's always occurring at that point. And at that point, the x coordinate is always positive 1. Okay, so we have cos of, you can think of it as 2 pi, or 4 pi, or 6 pi. You're going to have minus 1 times positive 1, which is minus 1. Okay, so when k is even, the slope is negative. All right, and so we've checked it out for when k is even. What about when k is odd? Okay, so odd numbers being 1, 3, 5, 7. Okay, so let's think about it in terms of 3, right? If we put the number 3 into this equation, we're going to have minus 1 to the power of 3 take 1, that's going to be 2. This number is going to be even. Okay, if you put 5 in there, we have 5 take 1 is 4. That's an even number as well. So the point of that is say minus 1 to the power of an even number is always going to be positive 1. Okay, so we have positive 1. And then over here we're going to have cos of either 3 pi or 5 pi or 7 pi or even just 1 log pi. Okay, and on the unit circle that's all of these values, isn't it? Okay, pi, 3 pi, 5 pi, 7 pi, 9 pi. And at that point, the x value is negative 1. So that's going to be 1 times minus 1, which is negative 1. So I'm saying k is either odd or even. If k is odd, then it's negative 1. If k is even, then this term evaluates to negative 1. So that's quite tricky. Hence, justify your conjecture in part D about the value of r dash of pi for any value of k. So we've made the conjecture. Yeah, I would say it's just talking about bringing it all together. And so here we've shown it, and so then it's just making a statement about it. So there when it says justify, we're going to say when k is odd, okay, the slope of the last term is minus 1, when k is even, the slope is minus 1. Therefore, every term, okay, every term that you add to it increases the slope by minus 1. So it's about just consolidating that. Part 4, as the number of terms becomes very large, describes what happens to the tangent. Okay, so that's why they're giving you these graphs over here. What's happening to the tangent there? Well, we can see it's getting steeper and steeper and steeper until it's a vertical line. Okay? What key feature does this correspond with? Asymptote. Doesn't exist at that point. Alright, so that's a pretty nasty one. Oof.
It's just slipped it on the mail.
Oh, it would have been perfect. It was like an hour and 3 seconds.